I know most of you, I'm not saying like all of you, most of you are here by, they say like, okay, it's better to take electronics, it's better to take computer science, it is better to take mechanical, and you follow it. Right? So like a movie review. If somebody gives a 3-star or 5-star to that movie, you'll go and watch. Correct? Yes or no? Correct? Till now, even if you had no intention of doing what you were doing, you just do it by the societal guidance, it is accepted till now. Right? But I believe all of you are above 18. Above 18. Right? So I believe this is a time you have to decide what you want to do. At least now you decide. Because all these days, nobody has, like, you have not decided like your lifestyle. You are guided by the society, and you went through the CBSE, English medium, and then like that's better school, this is a better school, and then like electronics in here, right? So happened is happened, because like even you were not considered to be that mature at that time, but right now whole country and society considers you as a matured guy, right? They have given you the voting power, right? So please decide why you want to do electronics. Why only electronics? There are two options. You select it and do it very passionately, or by default it comes to you, you do it by passionate. You have no option. It happens in all the stages of life. You want it, you get it, and then like you enjoy it. Otherwise, sometimes it comes to you by automatic. You have to enjoy that. You find your way to live this life passionately. Not by the societal drive, saying that like you have to get 4 S out of 7 subjects, or like you have to do only this, you have to do 90% and above. I'm not saying you should not do it, but you define by the societal drive again, or it is by your choice. That is what is my concern. Have you understood what I'm telling? Is it clear? Right. Now it is 9. Let's start. No block model better. Right. So my first guidance to all of you is that please decide what you want to do and why you want to do that. And try to decide from within on your own decision. You might fail once, twice, third time at least you will succeed. If you again go by the societal guidance, I'm not saying you should not go. Societal guidance is like this. They say like most of the ships are going in this direction. If you go in this direction, it will be better. Clear? So try deciding from within yourself. Search why you want to do this. What is your intention? I am here. If I do this, I am spending 3 years, like you have, all of us have a limited lifetime, right? 100 years at the maximum to maximum, right? If in that 100 years, if you are spending 4 years on this course, electronics, and finally you are joining something else, that's not your, you have watched the 3 Idiots movie? Ek gada tha usme, right? No, that's perfect. Okay? Do anything with a passion, with the interest of your own. With the interest of your own. Okay? Done. Coming back. All of you have selected electronics, and already in the second year, it is very hard to jump to some other things. So we got it already. We have to enjoy it. That's one aspect. Or like you're selected by your, let's consider you're selected it, but do it with passion. Right. This course, okay, my name is Harish Mekli. This is my name. That's my name, email and phone number. If anybody want to talk to me about the subject or anything that you want to wish, please call me within 9 to 9, morning 9 to evening 9. Right? Or you can send me a mail at that email ID. Right. Now we'll close it. Okay. This subject that I am handling is digital electronic circuits. The subject that I am handling is the digital electronic circuits. And I believe all of you have studied some part of this in the first year. Correct? Like logical gates, half adder, full adder. What else you have studied? Number systems. K-maps you have studied? Wow. Which 2 variable K-map, 3 variable K-map? 2 and 3 you have studied? So shall we jump directly to the 4 variable K-maps? All of you are comfortable? Okay, let's start from the basic. Same question again. What is that question? What we do and why do we do what we do? The question is, why do we do what we do? Right? If it is a subject is a digital electronics, you have to be on time. Please come. If subject is digital electronics and we study all the digital concepts here, why we have to study digital electronics? Why not analog electronics? Only analog electronics. I am not saying you are not studying analog electronics. You are also studying analog electronics. Why not only analog electronics? Why digital electronics? Why digital systems? Why not analog systems? Why not only analog systems? Is there a world that we exist? All things around us is digital or analog? All that it exists, not created by human, by default it exists. Like you say, like creation of a god. Is it analog or this, like the voice we are saying, like the movement that we are doing, analog or digital? Or it is the temperature that is changing? Everything is analog, right? Everything is by default analog. Why do we want a digital system then? Huh? Why do we want a digital system then? Consider analog is complex. What is the next point? Come. Right. Let's consider complexity as a point. Have you studied op-amps? Operational amplifiers? Okay. Anything you want to do with analog, op-amps are the ideal choice. Addition, multiplication, integration, differentiation. Anything, that mathematical thing that you want to implement on the circuit, analog side, then like op-amps are the ideal choice. Okay, let's consider op-amps are slightly complex than the logic gates. Logic gates are easy, right? Logic gates are easy. So with that example, we'll consider one point, complexity. Next. Precision involved, very, very important. Analog is more susceptible, like more prone to noise signals. If there is some noise, it can disturb the analog very easily. but digital, not that easy. So analog is more prone to noise. Noise in the sense, not the noise that we create in the class or in the market. So noise in the sense a different unwanted signal. It is also a signal which is not required right now. Some other time it might be required, like in the oscillators. Oscillator we require some noise so that it gets amplified and amplified and amplified and then becomes its oscillation. You're understanding? Anything as a noise is just unwanted signal right now, that's all. Okay? So second point is, analog is more prone to noise. So noise can easily corrupt the analog signal. Next. Huh? Accuracy, I will give an example. Cannot be exactly considered because analog is by default exists. We will convert that to digital. That means we are sampling it. When we sample it, we lose some parameters in the analog or some values in the analog. So we cannot say the accuracy is good in the digital. Next. More robust, no. That's a nice thing. You have to think like this. What all involves in the digital system, or you say any system, what all it involves? Normally what it involves is a system will take an input and gives output. Sometimes the system will have its own memory so that it will store the values. Okay? So when it has a memory, it is very easy to store the digital signals. It is very difficult to store the analog signal. Analog we have a simple option as a capacitor. You can store analog signal in a capacitor. But the problem is, by default all capacitors have the discharging phenomenon. Keep it outside but it will discharge. Right? This is normally happens in all the analog systems. So it is very easy to store the digital. Digital values you can easily store it. Right? Then like what we said, like complexity, noise, store, easy to process. See, we all like something like because it is easy, right? We wear this shirt and like this pant because like it is easy to wear. Why not dhoti? Right? It is an option we have, but like still we are adopted to this because it is easy. Right? We can easily manipulate the signal, process the signals coming inside to the system and then store it, then give the output, which is of less prone to noise, less complex system, easy system design, and values can be easily stored and easily processed. So it is the reverse order. Process, less noise, and then like easy to store, and it is less complex. Clear? So what are the advantages of a digital system over analog? These are the advantages. Please write it down. Disadvantages of digital systems over analog systems. Advantages of digital systems over analog systems. First one, easy to process, less prone to noise, second one, less prone to noise, third one, easy to store, fourth one, less complex. There are a lot of reasons. Right now we will restrict our discussion to only this. Okay. If these are the advantages, there has to be some disadvantage. You just cannot get only advantages, not possible. Anywhere you do, like you will not get only advantages. There has to be some disadvantage. What are the disadvantages? Accuracy is a disadvantage. Accuracy is a disadvantage. One point you write in the below that. A disadvantage is an accuracy. A disadvantage is an accuracy. We'll see, like, I'll give one example where in which you can visualize this problem of accuracy. Okay, right. Now we know this. Okay, now we have understood what are the advantages of this digital, but we also know that, like, all the things that exist around us by default creation, it is analog. The first thing that we have to do is we have to convert that analog signal to the digital signal. Then we have to give it for processing. Correct? Then how do we convert it analog to digital? Okay, what do you mean by what do I mean by a signal, right? Signal can be anything with respect to the time. Easy way to understand the signal is with respect to time. There can also be with respect to frequency. Right now we will not do that. Okay? With respect to time, I am trying to have the temperature in Bangalore. Okay? Morning it starts with some value and gradually it increases, and then, like, in the night it reduces. Correct? This is the temperature, we'll assume it. Like, this is the temperature signal with respect to time in the Bangalore in BMS. Okay? Now we have to convert this to the digital. Right? When I say, like, convert, the first thing that is required for us is like a sensor. A sensor which will convert this physical parameters like temperature, light, sound, these all the physical parameters, to the electrical parameters. What are the electrical parameters? We have only 5 electrical parameters. All your study in 4 years will revolve around only these 5 parameters. Voltage, current, RLC, not power. RLC, right? Any one of this changes, the others will also change. If resistance change, the voltage and current changes, correct? These are all related things. All these 5 parameters are related. We can use a sensor and convert these physical parameters like temperature to the electrical parameter, right? Like, one example is LM35, which is very cheap and available in the market for 20 rupees or something like that. What is the advantage of that? It is a linear sensor, meaning what? As the temperature changes, it gives a increasing voltage. Increases, as temperature increases, the voltage output of the LM35 increases. As the temperature decreases, it also decreases. So it linearly varies. It varies, the temperature is varying, like it is also give the same graph. You're understanding what I'm saying? That means temperature versus time now can be plotted as voltage versus time. Is that clear? Right? It is because it is a very linear sensor. It changes, the temperature is increasing, output voltage is also increasing. It is temperature is decreasing, output voltage is also decreasing. Clear? So this graph changing is clear. So physical parameter has converted to the electrical parameter. Now this electrical parameter has to be sampled to convert it to the digital value. How do we do that? We have 3-step procedure to convert it to the digital value. First is sample. Second one, quantization. It is actually sample and hold. Third one, digitization, right? This signal has to be sampled. Sampled in the sense I will take the particular interval in this, only this, and leave off this interval. This signal, leave off this part, leave off this part, leave off this. Like it goes on. Let's assume it till here. You're understanding what is sample? Sample is I'm taking the particular, at particular interval I'm taking the value. Another interval I am not taking the value. Okay? Have you understood the sample? Sample and hold is like we'll hold to this value. We'll have a small capacitor sitting after this which will hold this value. Right? And then it gives to the quantization. Quantization is the sense, if you see this, there is change in voltage at this interval itself. Right? Quantization is nothing but averaging it. Make it an average. And so that all this becomes square waves. Right? Digitization is giving a binary value to all these things. We'll take a particular sample of sine and then it will be more clear. Right now, have you understood what is sample and why it is required to hold? Hold is required because till it gets quantized, averaged, this value has to be held. Each value change in that sample value has to be held and then like it is changed or then like it is taken as an average. It is better you come to next class. Come. Today you please come, but don't try to do this next time. Yeah. Sample is clear. Sampling is clear. Only particular value, particular interval of time, and the rest of the time like we'll leave that signal. That is called a sampling frequency. How many times in the given time we are sampling it. The sampling frequency. We'll not deal in depth, but like sample you have to understand in abstract. This is the sample part. Clear? And then we will hold it because this has to be averaged. We'll have to take average and freeze it to a particular level. That is why we require hold. Then quantization is taking average. Right? Then digitization is giving a digit value to all this. We'll see the same thing with an ideal signal of sine wave. Okay. Why this? If I take only this sample, I can tell you only the numbers that are positive. If I take this sample, I can give you an example of positive, negative both. That is why I have taken this signal. Is that clear? Right. This is analog signal. Step first to convert it to the digital is to sample it. Yeah. I wish whatever I write on the board, you have to take it down. With an understanding. If you don't understand, you have, please question me. Right? This is analog signal. We have converted that to the sample the signal and we are holding it like sample and hold. Well, you can say just sample. If you don't give a import, like you don't understand the importance of hold, you just say sample. This is a sample signal from this to this. You can understand this, right? Next is what I do. We'll quantize it. This is the next stage. What we do? We'll freeze this. Right. This is quantization. You understood the difference between this and this? This and this you understood? If you see the signal here, from this to this it is varying. In this sample itself it is varying. Now I will give an average value to that. I will take an average and freeze it value in the middle. Clear? Then what is the next step? We have to digitize it. What do you mean by digitization? Is giving a value to it. This is digitization. Clear? Come to first bench. These three steps are clear with a diagram. Any doubts? No, right? It's easy. Continuous signal to sample to quantization, freezing the level, freezing level to the values to the each level. Now all of us have a mind saying that when it is digitized signal, then it is in binary. System is in binary. That is all of us we know. It is all about ones and zeros. Right? Give this binary value to this signal. Binary value to this signal. Okay? For this, there are a lot of coding techniques. There is hexadecimal code, there is octal code, there is a, what else you have studied? BCD is there, decimal is there. BCD and decimal are same thing. Binary coded decimal, right? Decimal we are coding it in binary, right? And what XS3 code, we'll discuss what is XS3. There is a gray code. You have used a K-map, right? In K-map you use a gray code. That is also a coding technique. So there are different types of codes, and these codes can be converted from one to another. If you are representing this using an hexadecimal or decimal signal values, decimal coding technique, you can convert that to the decimal or like octal or something else. You know how this conversion happens. You have studied it in the first year, right? We will not. Now what we have to do is, we have to assign some values to the signal, right? For that I want to know how many samples are there here, right? What I do is, sample here at this level and at this level is same. Only the difference is time interval. Are you getting this? This level and this level is same, only the difference is time interval. So I will call this as V1. This is voltage, anyway it is voltage. That we have converted from temperature to voltage, right? Then the second one I will call it as V2. The maximum one I will call it as V3. Similarly, V1. Right? How many samples we have? 3 exactly. The other 3 are complement of the original signal. We have only 3 signals, V1, V2, V3. The other 3 are complement of the original signal, correct? So what I do now? We need 3 signals, right? And we need another 3 as a complementary. In total we need 6, right? If we need 6 values, right? If I write like this, 6 samples are there in total. And we are very clear, these 3 are complement for these 3. This is if I assume V1, V2, V3, then it will be minus V1, minus V2, minus V3. We'll see like how it is, how is that going to happen. If I represent this in binaries, when I represent this in binaries, 0, 0, 0, I require 3 bits because 6 requires 1, 1, 0. 6 is 1, 1, 0, right? 8, 4, 2, 1. You remember? You remember? This is 4 plus 2, 6. Right? 5 is 1, 0, 1. correct? 4 is 100, 3 is 011, 2 is 010, 1 is 001, right? Now I will assign each voltage a value here. What is that? This I will assign it to V1, this I will assign it to V2, this I will assign it to V3, right? Next one, this one, I will assign it to minus, okay, not this one. We will assign this to minus V1. Why? If you take 1's complement, of 1, it is 6. 1's complement means what? Wherever there is a 0, replace that by 1. V2. Correct? Minus V2. 5 is, if I take 1's complement of 2, it becomes 5. Correct? The same thing. This is minus V3. 4. 1's complement to each other. But when you have 3 values or 3 bits, the maximum number that you can represent is 111. Using 3 bits, the maximum number that you can represent is 7. That is 111. This 11 is complementary of 0. That's where in binary, most of the time, it is considered as plus 0, minus 0. It is our conversion technique. How do we use this in the system? What you have to understand is, these are the values that I am going to use here. This signal I am giving it as, what is the value you have given? 1. This signal we are giving it as 010. This is 011. Minus V1 is 6. Minus V1 is 6, right? Minus V2 is this point as a 0 signal. Did you understand this? Any doubt in this? So what we have done, we have converted analog to digital, and we have the numbers for that digital values now. Is it clear? This is how we convert analog to digital. So this sample, I have taken 8 samples in total. These are 8 combinations. That's why I'm saying it as 8 samples. Otherwise it is only, no, correct, right? 4 plus 4, 8 samples. So I have represented in the binary format. Is it clear till here? From here we start number systems. From here we start number systems. Is there any doubt here? If you have any doubt, please ask me right now. This is the time, because analog to digital conversion will not discuss once again. And all of you, those who were in the lab, were asking like question, what is the meaning 0, 0, 0? It says 1, 1, 1. Right? Is it clear now? Right? Done? Huh. Then you have to increase the bits here. That's the thing. If you have more samples, there were only 6 samples, I have taken only 3 bits. Now if you have 9 and 10 and 11 samples till 16 or till 15, you can use 4 bits. More than 15, 5 bits. It goes on. No, complements are like standards. And like everything you take in here will be here. You are understanding what I am saying? Replication of each other, but it is a negative voltage. That's all the difference. Right, huh? Can't there be? Assigned values. No, I'm not getting your question. You are saying like already signals have been assigned a value. That's what you are saying? For what? Like if I increase the samples, then it is totally different number system. Well, 4-bit values will come for each of this signal. If anybody of you got No, that is your coding technique. This is digitization, is you are encoding this value in your system. You are designing a system. Then you will say like, okay, this voltage level I am going to code using 001. This value I am going to code this using this. This voltage value I am going to code this with this. Is it clear? It's your system. You have to code. Only the thing is that if you use this 8421, it will be ideal to convert back to the analog signal. Because higher the value, higher the weightage. Any other question? Right. Is it clear? Shall we go to the next step? Shall we go to the next step? Is your doubt clear? Your doubt is his doubt? But
actually the time period of V1 is greater than V2. But the amplitude of V2 is greater than V1. Which one would be the more effective one?
No, this depends on the voltage. Now whatever we are coding is depends on the voltage. This voltage level is less than this. That is why I have given the lesser number to this than this. Time period right now I am not considering. Just like if I do consider time period, all the signal analysis that I am doing, I have to consider with time, with respect to the time. This you will study in the signal processing. There are a lot of signal types are there, right? They will study with signal, a signal with respect to time. And there is one more subject, digital signal processing. You study two subjects. Only to understand like with respect to time and with respect to frequency, what is happening to signal. Okay? Right now what you understand is, you make it very simple. If you see it is like this. Or you always give this example. When we were child, first year, first standard, right? All of us have been told that sun rises in the east, correct? Correct? But what is exactly happening? Does really sun rises in the east? Earth rotates in the opposite direction. That's why we feel that like sun is rising in the east, correct? But if I tell this to the first standard kid, then like he'll get confused. That's why we make simple, right? In another side, sun rises in the east is true also. Correct? That's why we make systems very simple and give bit by bit. As you go on, you will try to understand the more complex system. Right now what you have to understand is, we will freeze this voltage values and assign the binary values to each of these voltages. That's all you understand. Is it clear? If you have some random signal, if there is an amplitude here, then you have to assign a particular value to that. That like depends on your choice. If it is, see, this I have taken it as an ideal case. This I have taken it as an ideal case. In no the practical systems, you will have exact square wave, not possible. It will always be like this, some random signal. In this case there is no, so you can assign all that samples to this directly. So this is what should I say? This is an unsigned signal, this is a signed signal. I can say like that. See, like this, I am saying this thing is an ideal thing. I have taken an ideal sample thing. It is not exactly, it will not be there always. What it is there in the real time systems or real exact system is there some random signal. You have to take and give the voltage value to all of this. These are all different voltages. It will not exist in reality. This is an ideal case. To tell you that like what is a mapping thing, I have taken the ideal case. It will know this, no sine wave is generated by all the practical system that exists by default. It is our consideration that okay, pure sine wave exists. We take it as an ideal system. That's why I mentioned it. It's an ideal system. This is all ideal thing. In practical, you will have some random values here. Some things which will not exist, even if it exists, for particular field it exists. The signal will be like this. You have to code this. right? That's the different thing, story. But like for your understanding, I have idealized it. We will assume it will be pure sine wave, sample, quantize, digitize, assigning a number value to that. Is it clear? These steps are standard. Is it clear? Shall we go to the next one? Right, done. When I say a number system, oh, shit. Let's try. Let's try to be faster. These are all things are binary. Okay. When I say binary, there are different coding techniques which are restricted to your syllabus. Let's restrict to your syllabus now. In your syllabus, you have to study BCD, binary coded decimal. Okay, like the systems operate in binaries, all of us we operate in decimals, right? Because we have been taught from the beginning that like 2 plus 3 is 5. In the decimal we have written. We have never written in the binaries. So this decimal number represented in the binary is called as binary coded decimal. In decimal we have the number from 0 to 9, only combination of this. Any other number is a combination of this, right? So when I say it is a BCD, it is from 0 to 9 only. Is that clear? Then the next one is hexadecimal. Hexadecimal number system. It ranges from 0 to 15. It ranges from 0 to 15. The next one is XS3. Normally we will have a BCD signal converted to the XS3. Meaning what? BCD is, this XS3 is only as a dummy example for you to understand there exist different types of coding. Okay. Normally the BCD signal ranges from 0 to 9. XS3 is ranges from 3 to 12 plus 3. BCD plus 3 is XS3. 3 XS. Clear? Then we have gray code. How do we write a gray code? It's a reflection of its own image. Have you, do you know this gray code before? No? Yes, right? Most of you might be knowing it. Okay, we'll write it anyway. So shall I rub this? What I said, like first one is BCD, then we have 4 different codings in your syllabus. We'll restrict only to that. There are a lot of coding techniques. We'll not worry about all those things. We'll restrict only to 4. Right. What is this? Like, okay. When I say it is a BCD, I said it is from ranges from 0 to 9. To represent 9, you require minimum 4 bits because it is 1001, 8421 coding. Right? So, wait for all of this. This I am writing with the assumption that you know 8421 meaning. This is 8 value, this is 4, and this is 2, this is 1. If you write 2 here, 1 here, in this column, that carries 2 value. If you write 1 here in this column, it carries 4 value. Now it is 3 because it is 2 plus 1. This is 2 value plus 1 value. 4 plus 1, 5. 6. This is 7 because 4 plus 2 plus 1 is 7. 8. 9. Right? In BCD you have number only ranging from 0 to 9. Why we have, then there is a separate coding called, okay, XS3 will write it. XS3 is 1, 0 0011. Same thing goes this as a 12. This as a 12 is 8 plus 4. You have to add 3 and write it. The representation of XS3 is in the hexadecimal coding. We'll see like what is hexadecimal coding now. All 4 values are covered. Okay, guys, let's see to this. All of you please see here. How do we write 10 in decimals? BCD? 1, 0, 0, 0, 0. We require 5 bits to represent a 10 in the BCD. One zero? Acha, that is hexadecimal. There is a difference between decimal and hexadecimal. Decimal, you have the 10 representation as 1, these 4 zeros. In the hexadecimal, it will become 4. Because you do not have, this is each single digit representation. This 4 bit will represent single digit. Digit in the sense 0 is 1 digit, 1 is another digit. We have the single digits in the decimal system from 0 to 9. In the, once I make it as 10, this requires 4 bits, this requires 4 bits. Another 4 bits I am not considering because this side it is 0, that is why I said it is a 5 bit. Is it clear? Please understand this. To represent 10 in BCD you require minimum 5 bits. Minimum 5 bits. Right? Ideal case 8 bits. Minimum 5 bits. Is that clear? Please understand. In hexadecimal it is 1010. Because hexadecimal number system from 0 to F. F is 15. 15 in the decimal I am saying. Is it clear? For all of you? Right, done. So if I write this 001 till 9 it is same. So we'll freeze it till 9. Till 9 same as BCD. Till 9 hexadecimal is same as BCD. Right? After 9 how do we write 10? This is 10. 8 plus 2 is 10. 11, 12, 13, 15. Is it clear? Now you ask me the question. Why hexadecimal is required? Have you understood? If you are designing a system with 4 bits, you can optimize your system using a hexadecimal, not using BCD. Because you will get like 15 codes. All these codes to represent different voltage levels. You have only 9 samples, means 10 samples. Is that clear? Is that clear for all of you? So that's where the hexadecimal impacts come. And most of the things we discuss from now will be in the hexadecimal. Until and unless we mention we want it in a BCD, it will be in hexadecimal. Is that clear? What is the importance of hexadecimal? In 4 bits here we will have only 9 samples. In 4 bits here we have till 15 samples. 17 is again, this is done, right? It has maximum of 15, right? 17 if I assume that is in hexadecimal directly. This is 1 and this is 7. Is that clear? If I assume that in hexadecimal directly, I have no other option. This is frozen now. The maximum value that I can represent using 4 bits and hexadecimal is 15. The next is this 1 and this 7. Same concept. Same concept. Each digit will change. Is that clear? What is the option I have? The maximum representation we can do only 15. See, there are only 16 samples. I can give the value from 0 to 15 only. If it is 16, 16 is combination of 1 and 6 here. Same thing. Is that clear? Right, done. Shall we go to the next one? Agree to this. Please write whatever I am writing on the board, at least with some understanding you have to write it down. You feel right now you are understanding, but when you go back, when you try to read a book, like you might get confused, so that like it is better to refer it and then get it. Okay, right. Gray code. Please see to this. All of you, guys listen. The gray code starts from this. This is standard for, the 2 bits is standard for everything. Once it 2-bit is freeze, then like we'll take an image here, reflection image here. That 1 is this and 0 is this. This 1 will come here and 0 will go here. It is like you are folding at this point. You fold it. So that like if you're done this with painting, that paint will come here, right? Mirror image. This is called the mirror image. Okay? And the second bit level, you have to make it as 1, 1. It was 0, 0 here, you have to make it as 1, 1 here. Is that clear? The rest of the bits you keep it as it is because I was dealing with only 1 bit. So I can take the second bit in this case. Now, in all the 2 bits case, 1 bit case is over here. So 2 bits it will come here. Maximum 2-bit representation is 4 values. I have done the 4 values. Then again I have to take the mirror image. What is the mirror image value? 1, 0, 1, 1, 0, 1, 0, 0. Clear? This I have folded it. This is the mirror image now for 2-bit value. The remaining this thing, 1, 1, 1, 1. 3-bit maximum representation is over. Then like I have to go for mirror image of this. 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0. Okay, we have to continue this. 0, 1, 0, 0, 1, 1. Hey, 1 second. In this case, 3rd bit when we consider, we have converted these zeros to 1. 4th bit we have to keep it as it is. Correct? Correct? Then like now like 0, 1, 1, 0, 0, 1, 0, 0, 0. This 0, 0, 0, when I fold it at this point, it will go and overlap this. Correct? Now all these are zeros, now you make all these are 1. This is how we write a gray code. Is that clear? This is a reflection code. This is also called as reflection code. What's your next class? Right. Is there any doubt in this? Gray code, hexadecimal. Okay, BCD doubt is clear. BCD doubt is clear. It is not 1010 in BCD. It is this in BCD. 1000. Right? Clear? So once we studied a number system, this is a number representation. Right? What is the next stage? You have understood conversion from analog to digital and digital representation in the coding, that is binary coding, and we have different options in the binary coding. You can use any one of this to represent a signal level, right? Once you have studied a numbers, what is the next stage? Huh? Addition, subtraction. That's what you have studied, right? When you were kids, like it has been told 0, 1, 2, 3 up to 9, like then you 0 plus 1 or 1 plus 1, 2 plus 1, you'll start from there. Okay?